Okay, my video cut out. So I'm going to do this video in two parts anyway, because I think the last one's 28 minutes, and I believe YouTube only allows me up to 30 minutes per video. Not sure on that, but we'll find out. So back to this problem number 55. Excuse me. This is our function. We can easily factor the denominator. Okay, and there's a couple of things I know, and I always look at asymptotes first. It's just a Mrs. Wilson thing to do, but you can find the intercepts first, you can find the asymptotes first. It really doesn't matter what you do first as long as you get everything there. Okay, so we want to sketch the graph of this thing without a calculator. So what I know is that I'm going to have a vertical asymptote at x is equal to positive 2 and x equals to negative 2, because I set my denominators equal to 0 and solve. I know I'm going to have no horizontal asymptotes because the degree of the numerator is bigger than the degree of the denominator. And slant asymptotes, I know it's going to exist because the degree of the numerator is exactly one more than the degree of the denominator. So that means I need to divide and find that equation. So I have x squared minus 4 going into x cubed plus 0x squared plus 0x. Because remember, I've got to fill in 0 times x to the next power down all the way till, you know, I'm at the very last x, or the linear part, x to the first, which is right here. So let's divide. X squared goes into x cubed, x times, and that's a 3 right here, cubed. X times x squared is a positive x cubed, but I'm going to change the sign. And x times a negative 4x is a negative 4x, but I'm going to change that to a positive. And you notice this is 4 times x, so I'm lining this up here. And those are going to cancel, so I'm going to bring down what's left. That's 0x squared plus 4x. And I'm going to repeat the process, right? Except when I say x squared goes into 0x squared, it goes in how many times? 0. So what I'm left with is, you know, if you want to, you can do this. 0 times x squared is 0x squared. Well, nothing from nothing leaves nothing, and we're left with this 4x. 0 times negative 4 is a negative 4. So the remainder is 4x minus 4 over that denominator, but we don't need the remainder. What I know is that my slant asymptote is going to occur at the line y equals to x. Okay, so I have all my asymptotes done, and in fact, I'm going to move this over. Sorry, my dog's drinking water. And I'm going to plot those asymptotes to get them out of the way, or sketch them. So at x equals negative 2, I've got a vertical asymptote. At x equals to positive 2, I've got a vertical asymptote. And I've also got a slant asymptote, the line y equals to x, which is this one here. Okay? So that looks pretty messy, but it's not bad. Now I'm going to find my intercept. You know, when x is 0, what is y? Well, if I plug a 0 into my function, I have 0 divided by negative 4, which is 0. So I'm going to have an intercept, get another color here, at the point 0, 0. That's my y-intercept. Okay? For my x-intercept, it's going to be, I'm going to let y equal to 0, or let the numerator equal to 0. Well, x cubed equals to 0 means that x is equal to 0. So the x and the y-intercepts are the same. It's the origin. Okay, so I plotted that right there. So my asymptotes are sketched onto the coordinate plane. My intercepts are there. And so now I have to plot a point between and beyond each x-intercept and vertical asymptote. Okay, so here's a vertical asymptote, and I don't have a point here. I don't know if my graph's going to be in this region or where. So all you have to do is just make a little xy table and say to yourself, you know, what if x equals to negative 3? Well, if I plug a negative 3 into this function, I get negative 3 cubed over negative 3 squared minus 4. Negative 3 cubed is negative 27. Negative 3 squared is a positive 9 minus 4, which is negative 27 over 5. Right? So what that is, it's I got to move down 5. So I go over to negative 3 and I go down, 5 goes into 27 5 times, right, with a little bit left over. So I'm going to go just a little bit past 5 and I'm going to plot a point. Why? Because I know my graph's going to be in this region. All right, and what I know also, so, you know, this is going to be a little bit off because my spacing's not perfect here. But what I know is that if this is the point negative 3, negative 27 fifths, my graph's going to get really, really close to these asymptotes like this. Okay, I only need one point. Now I should choose a point to the left of this x-intercept, so in between this vertical asymptote and that intercept. So I can let x be, let me fill this in, let x be negative 1. If I plug a negative 1 in, I get negative 1 cubed over negative 1 squared minus 4, which is negative 1 over 1 minus 4, or negative 1 over negative 3, or positive 1/3. Okay, so at negative 1, if I go over to negative 1, I go up about positive 1/3, and I've got a point there. And I'm also going to choose, I wrote a half, that's supposed to be a 3. And if I choose, now I'm going to choose one between this intercept and this vertical asymptote, so I'm going to choose 1. If I plug a 1 in, I have 1 cubed, which is just 1, over 1 squared minus 4, so that's 1 over negative 3, or negative 1/3. This is important, so negative 1/3 is about here. Now remember, my graph has to be a smooth curve, and it has to head toward these asymptotes. So I'm just going to sort of let the asymptotes guide the graph, something like that. Now I've got to find a point to use to the right of this horizontal. So that's what I mean when I say a point between and beyond each x-intercept. So these are points between this x-intercept and beyond each vertical asymptote. So I'm going to choose, this was negative 1/3, I'm going to choose when x is 3. If I plug a 3 in, I'm going to have 3 cubed over 3 squared minus 4, which is 27 over 5. So it's positive 5 point something, so it's up here somewhere. And again, because I know my graph has to hug those asymptotes, it's going to go something like this. So, you know, remember this asymptote kind of keeps going on forever. So the graph of the function, or the sketch, is going to look something like that. That's just from having the intercepts, the vertical, horizontal, slant asymptotes. I can sketch the graph. And if I put this function into the calculator, so you can see, we've got x cubed divided by x squared minus 4. Oops, minus 4. Okay, so I'm putting it into the calculator. And if I hit the graph key, there's the function. So here's my sketch, which, you know, isn't perfect by any means, but the graphs are very similar. The graph parts are in the right places, okay? The asymptotes vertically are clearly seen. And while it's a little flatter here and mine's not quite as flat there, it's okay. I know my graph's headed toward those asymptotes. So the graph always has to hug the asymptotes. Let's do one more. Let's do number, I don't know, let's do number 52 from the book. So this is x squared over x minus 1. Again, I'm going to look at my asymptotes first. Okay, I know I have a vertical asymptote, the line x equals 1. I know that there are no horizontal asymptotes, and I know that I have a slant asymptote because this degree is bigger than that, so I'm going to divide. X goes into x squared x times x is x squared, change the sign. X times negative 1 is negative 1x, but I change the sign to positive 1x. Those cancel, and I'm left with x. All right? Do it again. X goes into x positive 1 time. 1 times x is positive x. I'm going to subtract x to change the sign and cancel it out. And then 1 times -1 is -1, but I change it to a +1. So that's my remainder. So my slant asymptote is the line y equals to x plus 1. X-intercepts. I take the numerator, set it equal to 0, so I know that x equals to 0. So I've got the x-intercept at the origin. And for the y-intercept, I plug a 0 in for x. So guess what? I'm going to have 0 over -1, which is 0. So again, my intercepts are at the origin. That's not always the case, but in these two cases it is. So I have my intercepts and my asymptotes. So let's go ahead and plot those on the coordinate plane. Do 1, 2, 3, 4 in all directions. Trying to keep my little tick marks here as evenly spaced as possible, but doing this freehand is really hard to do that. Okay, I know I have a vertical asymptote at x equals to 1 because we already solved that, so there's my vertical asymptote. And I know I have a slant asymptote at the line y equals to x plus 1, so I plot the y-intercept, which is 0, 1. And I go up 1 over 1, so my slant asymptote looks something like this. Okay, I'm also going to plot my x and y-intercept, which is the origin. And now I've got to sketch the curve. And again, I need to go between and beyond. So I need to go beyond the asymptote. So beyond this asymptote on this side, I'm going to make a little table. I'll let x equal to -2. Well, if x is -2, my function was 2 squared over, -2 squared over -2 minus 1, which becomes 4. -2 minus 1 is -3. So -1 1/3 or -4/3. Okay. I have a point in here, so guess what? I already know part of my graph's going to be in here. I'm going to use this intercept and just sort of follow the graph like that along the asymptotes. Okay. Now I need to check a point in here. So I'm going to choose x equals to 2. I plug a 2 in, I have 2 squared over 2 minus 1, which is 4 over 1, or 4. So when x is 2, y is 4, I've got a point up here, so guess what? I know my graph's going to be up there. I don't need another point. I know it's going to swing toward those asymptotes. And I'm done. And again, if I want to verify that with my calculator, I just have to enter the original function, which was x squared divided by x minus 1 into the calculator and hit the graph key, and there it is. Okay, you can see at x equals 1 there's a vertical asymptote, and at the line y equals x plus 1 there's a slant asymptote. Alright, so the homework's up on Edsby. I would highly suggest that you try doing those odd problems. That way you can check your answers in the back of the book and let me know on Thursday if you have any questions. Okay, I don't think I'll be doing 2.7 tonight, but I will get to it tomorrow after work. It's been a long day. I've already been working for like 13 hours at this point, so I'm going to go visit my family. So have a great night, and we'll see you on Thursday.